Alright, so Gauss's law is a law of nature used to find electric field by exploiting symmetry, given by this here equation. Looks like witchcraft, so just sit there while I explain something to you that you should definitely already know. An electric field, E equals F over Q, is really how much force some particle of charge Q feels in this electric field. Let's go deeper so I can boast to you about how much about this topic I know. E is also known as kq over r squared. This looks vaguely familiar. Why? Like Coulomb's law. Oh my god, I am so surprised. Let's do some math magics and cancel out a bunch of stuff, and there you go. E is equal to kq over r squared, thus proving that electric field strength is not dependent on the quantity of charge Q. Alright, so electric flux is the amount of electric field that goes through a surface. The other part of this equation, Q enclosed over epsilon naught, is the amount of charge enclosed in a surface divided by the permittivity of free space, which is about 8.85 times 10 to the negative 12 in Coulomb squared over Newton meters squared. Alright, now let's solve an example problem. Yay! Let's say that we have two infinite planes with uniform charge density sigma. Using Gauss's law and some math magics, we can get to the right answer. What is E? And I'm assuming that you don't care about whatever the explanation is, so here's my work. So once we figure out that E is a constant and the integral of dA is equal to A, we get EA is equal to Q enclosed over epsilon naught. Once we find the density of sigma, then we get Q is equal to sigma over A, and once we cancel out everything else, we get E is equal to sigma over epsilon naught. Yay, we did it. So what this means is that the electric field of any point on the two surfaces of the planes is equal to sigma over epsilon naught. Alright, last example, I promise. Let's consider a thin hollow sphere with uniform distributed charge. What is the electric field when r, the radius, is less than a? So we set up Gauss's law again with the equation and proportion given to us. We can find out that E is also a constant and EA is equal to the Q enclosed. There is only 1 point charge of charge Q, so Q enclosed is equal to Q. That means that EA is equal to Q over epsilon naught area, and that gives us a final answer of 3Q over 4 epsilon pi r cubed. This means that the electric field at any point inside the radius less than A is equal to E. So pretty much the only real-life application of Gauss's law in physics lies in using it to calculate the electric fields of a bunch of different shapes and scenarios. So to sum it up, Gauss's law is a law of nature that we use to find electric fields by using a bunch of math and equations. Combined with Faraday's law of induction for predicting how a magnetic field will interact with an electric circuit, and Ampere's law, these laws combine to make up the Maxwell equations. Yay, now we get to talk about the process of induction. In the induction process, a charged object is brought near but not touched to a neutral conducting object. The presence of a charged object near a neutral conductor will force inducing electrons within the conductor to move. The movement of these electrons leaves an imbalance of charge on opposite sides of the neutral conductor, so while the overall object still remains neutral since nothing has been transferred, there is an imbalance or an excess of positive charge on one side of the object and an imbalance of negative charge on the other side. And so once the charge has been separated within the object, a ground is brought near and touched to one side of the object, which allows electrons to flow from the Earth into the object, considering that this is a positively charged rod. Afterwards, the electrons move and disperse evenly through the object, meaning that there is an excess of electrons now, which forces the electroscope to open up as the electrons repel each other. Here you can see the same thing occurring with a negatively charged rod. The electrons and protons are forced each to one side, and then a ground is brought in, but this time the electrons will leave through the ground into the Earth, and now there is a positive imbalance in the object. Once the electron rod is moved away, the positive Protons will disperse and the object is now positively charged through induction. Here is an actual example of a glass rod and silk experiment, which makes a negative rod put to an electroscope, and once the electroscope is grounded, the same thing will happen theoretically, and the electroscope will begin to repel itself. In real life, thunderclouds frequently have a negative charge which repels electrons in the earth below, resulting in induced positive charge in the ground beneath the cloud. When the difference in the charges is great enough, this results in a massive flow of charge into the ground, which is exactly what thunder is. Other real-life examples include attracting paper with a rod, or using that same rod on a running stream of water to attract it, like Mr. Tran is attracted to Miss Heaton. So in the end, we've covered Gauss's law, which is involving magics, and the process of induction, which is charging objects without actually touching them. Yay, the end. Okay.